All right, so let's go ahead and start. We're looking at some operations with matrices today and tomorrow. And just a little bit of a review. Remember, a matrix is simply a rectangular array or arrangement of numbers. And those numbers we call elements. We're going to use that term a little bit more as we talk about the operations. All right, so every number that's in a matrix is called an element. Also, when we name a matrix, remember we're going to name it with a capital letter followed by its dimensions, okay? And we always put the number of rows first and columns second. So, for example, here we have matrix A, and it has 3 rows and 4 columns. So we would say it's a 3 by 4 matrix. The dimensions are 3 by 4. C is the same way. We have 3 rows and 4 columns. Matrix B, on the other hand, has 4 rows and 3 columns. So we'd say it's a 4 by 3 matrix. All right? So we'll name the matrix with a capital letter followed by its dimensions. And by the way, the plural of matrix is matrices. Matrices. And replace the X with the CES. Okay? So, yeah, it makes total sense, right?
Oh, yeah.
So, it's, I think it's a Latin.
Yeah, I think it's a
From the Latin, so you can blame them. Alright, well let's talk, before we look at actually doing operations, let's look at how we could come up with a matrix given certain data. Alright, so I'm going to give you an illustration here of a car manufacturer, and they have 2 different assembly plants, and they're assembling 2 different cars. Okay? And then, in order to assemble those 2 different cars, they broke it down into 2 steps. One is actually putting all the pieces together, assembling it, and the second step would be then painting it. Alright, so let's say that we have this data right here. Okay, each car requires a different number of hours for assembly and painting. So here we have plant A, and it's going to produce 50 of whatever car 1 is and 70 of whatever car 2 is. Alright? Plant B is going to produce 60 of each type of car. Alright, so that's raw data that we know. Then over here, as we're producing a car, it takes 3 hours to put car 1 together, to assemble it, and it takes 4 hours to paint it. Okay? Whereas car 2 must be a little bit fancier because it takes 5 hours to assemble and it takes 7 hours to paint. Alright, so here we have 2 related sets of information. And what's nice about this is we can then take these tables of information and we can write matrices for them to represent them. Okay? Yes?
Will they give us the tables or we have to derive them?
Well, no, I mean this is just information from a problem, so you could, you'd be given information. Now, what we can do, I'm gonna make 2 matrices, matrix C and matrix D. Okay, and matrix C is going to represent the plants by their cars produced. Okay? The plant by car matrix. And this is the thing, when you're dealing with a situation, you can name it and you recognize that the rows and columns stand for particular things. Alright? So, knowing that the number of rows comes first, okay, we have 2 different kinds of plants and we have 2 different kinds of car. So this is going to be a 2 by 2 matrix. Okay? So when we write the matrix, it's actually going to look just like our table. It's just formatted a little different. Plant A produces 50 of car 1 and 70 of car 2. Plant B produces 60 of car 1 and 60 of car 2. Okay? So now we have the same information, but it's in this structure of a matrix, so that later on we can actually do some operations with it. And we'll actually talk about that in a moment, using these two together actually. Now, matrix D I'm going to make with a car by hours matrix. Alright? Now again, there are two different kinds of car, so there's going to be two rows, and there are two different hours that we're talking about, hours assembling and hours painting. So it's a 2 by 2 matrix again. And it's going to look like this, 3, 4 in the first row, because that's for car 1. And the rows in this case are cars. And car 2 is 5 and 7. Okay? So you'll see here, again, we're able to represent information without having to write out all the words and things. Okay? Now, how is it useful, or why is it useful to do this? Well, we'll see in a little bit. If I wanted to, let's say I wanted to increase the production time by 20%, okay? I could do that just with the matrix rather than having to go to each one separately and do 4 separate problems. Now, you end up doing all the same math, but it's all within the same structure, so you're only having to write out the work once. Okay? Another thing that I could do is I could say, okay, well, I'm looking to hire people. If this is my production, and this is how much time it takes to make each car, then how many painters should I hire? Okay. Well, in order to know how many painters you should hire, you have to know what?
How much time do you want to do?
Total
How much
hours.
do you want to do paint?
How much time, the total hours painting you're going to have to spend at each plant, right? And this is where an operation we're going to look at tomorrow comes into play. If we multiply these two matrices together, C times D, notice this is plant by car, and this is car by hour. Okay? We'll talk more about this tomorrow, but when you multiply these together, you get a matrix that gives you the plant by hour.
What size of the
Okay.
matrix
So it's
would be?
50 times.
It actually will end up being a 2 by 2 matrix as well, but look at what the information it gives us will be. Okay, this is what you'll get, and we'll see tomorrow how to actually get this. But when you get 660 right here, this is talking about, it's a plant by hour matrix. So this is plant B, and this is hours painting, right? So at our assembly plant B, we need to make sure we have enough guys so that we can do 660 hours worth of painting every week. Okay, if these are weekly numbers. Alright, so, you divide that by 40, what do you get, like 16 and a half? So we're going to need 16 or 17 painters in order to have enough hours in order to actually produce the number of cars we want. Does that make sense?
Yeah.
Alright, so we've taken two different tables of data, and by using matrices, we're able to now figure out some other things. Okay, and again, we'll do more with the multiplication tomorrow. But I just wanted to kind of motivate the whole thing here, so that you guys can understand where we're headed with some of this. All right. So let's talk about our first operation, matrix addition. Okay, matrix addition. First of all, just like we had with vectors, okay, we're dealing with something that's not just real numbers. It's in a structure now. A vector, we had the components we were dealing with. Here we have elements that we're dealing with in our matrices. So anytime you're dealing with a new structure like this, you have to redefine your operations. So first of all, in matrix addition, the question we're asking is, when can we add two matrices? And the answer is, only when the dimensions are the same. Okay, so if I have a 3 by 4 matrix, what kind of matrix can I add to it?
3 by 4.
A 3 by 4. Alright? You can't add a 3 by 4 matrix with a 2 by 2 matrix. Now, how do you add two matrices together? Okay? What you're going to do is you're going to add the corresponding elements. The elements that are in the same positions. Right? And the result is going to be a matrix that still has the same dimensions as what you started out with. Okay? So, you'll notice here, matrix addition is a lot like vector addition. Vector addition, we added the horizontal components and we added the vertical components. Here, we are dealing with matrices that usually have more than just two elements to them. Okay? But you're going to add the corresponding ones together. Alright? So, before we look at specific examples, go ahead and write down these three matrices as you're taking notes, because we're actually going to use these same three matrices throughout the rest of the day as we do some examples, and then we'll also use the same ones tomorrow when we look at matrix multiplication. So you'll have them once and you won't have to copy them over, we don't have to make up new ones every time. Okay? So take a couple minutes and write these down. Okay? Alright, so based on our rules, which of these matrices are we able to add together? A and C. Okay? They both are 3 by 4 matrices, so we can add those together. So let's look at how we would go about doing that. Okay? If I have matrix A plus matrix C, we said that you add the matrices by adding the corresponding elements. Alright, so let's look at what that means. Alright, every element has a position, okay, and we give its position based on what its row number and what its column number is. So this 3 right here, we would say is in position 1, 1, because it's in the first row, first column. Alright, so as we look over here at this matrix, the 7 is in the 1, 1 position. So we're going to add those because they're in corresponding positions. 3 plus 7 is 10. Okay? Then we can look at the element in the first row and the second column. That's position 1, 2. Alright, so over here, first row, second column, that position is 1, 2. So I'm going to add the 2 and the 6 and get 8. Alright, and I think you guys get the hang of this here. Alright, we're going to add the 4 with the 5 and get 9. And then the negative 5 plus the 4 and we get a negative 1. And you'll notice now our first row is complete. Okay, so now we have the next two rows. So I add the 6 with the 3 and I get a 9. I add the 3 with the 2 and I get a 5. The negative 1 with the 1, I get a 0. And the 7 with a 0 and I get 7. Okay? And then we do the same thing with the last row. Again, this is the third row, first column, so it's position 3, 1. Over here, third row, first column, position 3, 1 is the negative 1. So negative 2 plus negative 1, we've got a negative 3. Negative 3 and negative 2 is negative 5. Negative 4, negative 3 is negative 7. And 9 and negative 4 is 5. So that right there gives us the sum of those two matrices. And notice we ended up with a 3 by 4 matrix, just like we started with. Okay? Any questions so far? Alright. So relatively simple concept, however, if you're sloppy, you're going to mess up. Okay? You're going to add the second row number with a third row number or something like that. Okay? So just be neat and be careful. Okay. The second operation that we're dealing with is what's called scalar multiplication. What's a scalar? A number. Okay? It's just some real number. So we're multiplying of a matrix by a number. Okay? So here, you can multiply any matrix, no matter what its dimensions are, by a number. Because when we multiply a matrix by a number, we're simply going to distribute that number to every element in the matrix. Okay? So if we want 13b, we just take matrix B and multiply every element by 13. Okay, so we get, 13 times 1 is 13, and 13 times 5 is 65, and 13 times 6 is 78, and so on. Okay, there's our first row, and then we do the next 3 rows the same way. So what's 13 times negative 2? Negative 26. What's 13 times 3? 39. 13 times 8? 91. Okay. Wait, no, sorry. Oh wait, that's 13 times 7, sorry. 13 times 8 would be 104. Okay. And then 9 times 13, do you guys know that one?
117.
117. Okay, good. 117.
I don't know,
You just multiply it by 10 and take 13 off.
Okay. Yeah. And then times 0 is 0, times 1 is 13, and times 2 is 26. So there you have 13b. Okay? Yeah. Now, going back here, let's think for a second. I mentioned this What if I wanted to increase production by 20%? What would I do with this
Times 1.1.
Times 1.2.
times a 1.2? Okay, if I wanted to increase by 20%, I could do 1.2c. And that would give me the matrix with 20% more production. I could then see what that would equal. Okay? So, alright, so let's try one here where we put them together. Okay? 2a minus 3c. Okay? 2a minus 3c, especially starting out here. Let me make a recommendation. Don't try to get your final answer all in one step. Okay? Figure out what 2a is. And then we're going to add that to a negative 3 times c. Okay, I'd recommend distributing the whole negative 3 in. Okay? You can do it just distributing 3 and then you subtract the corresponding elements, but it's really just preference. I would recommend doing it this way. If you can get them.
And at the end, you still want us to get the, do you want us to get the 1, 0, 0, 0, 1, 0?
No, we're not solving a system here. We're just adding the matrices here. Okay. Your solution should just be, single matrix.
Negative 10 plus negative 18. Oh, my bad. I read the same.
Let me see your. I'll check it. Check it. Ooh. Ooh. Do you know this? We can have the entire last class. You're actually correct. It's probably just you.
Yeah.
Actually, I have all the answers, so it's kind of not me. It's you. So.
Oh, I got it.
Yeah. Just add them together. Take it back.
Mr. Rickson, of course you did. Mr. Rickson, can you go to the rest? I finished.
What is it, negative 1?
Yeah,
I want chocolate right now. Oh, right now. Honestly. That's 12. I was like, R.
Yeah, it's
All real numbers.
All real numbers. There we go. Alright. Alright.
Don't go there.
So that's what you ought to get when you do the 2 times A and the negative 3 times C. And now we can do our matrix addition.
Subtraction.
So does someone want to give us their first row? Nico?
Negative 15, negative 14, negative 7, and negative 22.
Alright. Good. Okay. So want to give us the second row?
3, 0, negative 1, 14.
Ooh.
What was the last? Oh, 14?
I'm just kidding, it's negative 5.
Negative 5? There you go. Okay, good. And how about the last row, Jacob?
Negative 1, 0, 1, 30. Of course.
Alright, good, good. Okay, so any combination of these, you just find the multiples first, then add the corresponding elements together. Okay? Alright, good. Now, I do want to talk about one more thing that your book doesn't actually cover. Okay?
Here's the interruption. Nico Linzer, please come to the 400 building main office. Nico Linzer.
Almost.
It's not one of your last names.
No.
It's funny, I'll hear people like say something about somebody and not realize that it's actually one of my students because it's a different last name than I'm used to calling them. Anyways.
He has a K. Nico has a K. So
Oh, does it?
Yeah.
Is
Okay.
that the little one that was in our math class last year?
Nope.
No, you-
That's
Okay.
this Nico.
Yeah, no, there was a little one.
Rodrigo.
No, that one.
Anyways, let's take a look at transpose matrices. Okay?
Little brown.
A transpose matrix. The question is, what if we really want to take the data that's in A and put it with the data that's in B? Okay? How do we do that? Well, sometimes there's no way that we can. Alright? But using a transpose matrix, we actually can combine A and B together. Alright? And the reason is because a transpose takes a matrix and it reverses the elements, it reverses the coordinates of every element. And therefore it also reverses the dimensions of the entire matrix. Okay? So, here's some notation that you haven't seen yet before, but element A sub jk becomes element sub kj. Alright, so, let's take this 8 right here in B. Alright, the element 8 is in the second row, third column. So its position is 2, 3. So when I transpose B, it's going to go into the third column, second row. Or I'm sorry, third row, second column. It's in the second row, third column. It's gonna be in the third row, second column.
Is there a way to think of it as like a rotation?
Yeah,
No.
like, you like flip it.
More like a reflection, actually.
So like,
Okay? It's almost like we're taking this matrix. If you draw a line straight between the top left and bottom right, which are the two that stays put, and you reflected this across that line, you'll get your transpose. Okay? So, let's look at that. Notice the dimensions end up the opposite, and here's what the notation would look like. Okay? If we did matrix A, we would use A, and that's a capital T, or if, depending on what book you read, you might see a lowercase t. Doesn't matter. But if it was a 3x4, it's going to end up a 4x3. When we have B as a 4x3, when we take the transpose of B, it's going to give us a 3x4. Alright, let's step through that. Okay, let's step through that one piece at a time. Alright, the element that's in the first row, first column, if we reverse the coordinates there, where's it going to be?
The same place.
In the same place. Alright, so that 1 stays put. The 5 is in the first row, second column,
so do 2, 1.
so it's going to move to the second row, first column. Good. The 6 is in the first row, third column, so it's going to move to
3, 1.
third row, first column, 3, 1. Alright? So you'll notice the first row now becomes the first column.
So you just, everything after that, you see.
Everything else is going to act the same way, okay? So this second row is going to become the second column. The third row becomes the third column. And the fourth row becomes the fourth column. Okay?
When is the test? Is it next week?
It'll come sometime soon here. So
I'm ready.
So we're thinking about getting over with.
alright. Let's try C transpose, okay? So C transpose. What are the dimensions gonna be?
4, 3.
4 by 3.
Okay.
Okay. So what's our first row?
Seven.
It's 7, 3, 1. Negative 1. Okay?
6, 2, negative 2.
Good. 6, 2, negative 2, and so on. 5, 1, negative 3. The third column becomes the third row. Fourth column becomes the fourth row. 4, 0, negative 4. Okay? So be careful. Alright? And why do we do this? Because remember, we couldn't do A plus B because their dimensions were different. However, if we transpose either one of those, we can add it to the other one. A plus B transpose we can do because that'll give it, they're both 3 by 4 matrices. We could do A transpose plus B because those are both 4 by 3 matrices. Okay? Alright?
Realize.
Yeah, we had.
Yeah, I get real creative when I make
That was
matrices.
pretty good.
So,
You probably wrote that and then transposed it and made that C.
I don't think he's.
Wait,
It still makes sense though,
Yeah,
like
it does.
this normal.
yeah.
Never mind. Just-
Anyways, so what we're gonna do for the remainder of the time, we've got about 20 minutes left. I want you guys to get some practice in on this. Alright, I gave you a couple of different kinds of problems, alright? First one's, this one is just kind of thinking if these are the same matrix, what would X, Y, and Z have to be? Alright, so a little bit of logic work there for you.
Okay.
Here, you're doing some basic operations. Matrix addition, some scalar multiplication mixed in there as well. Be careful with your parentheses and with your arithmetic. 21 to 24 are interesting because there we're solving for matrix X. So you're going to get an answer in the equation, but it's going to be a matrix. And then 77 is a quick application problem. Alright? So, go ahead and get started with this. Number 4, 13 through 16, 21 to 24, and then 77.
I have a question.
Okay?
Can we use the board?
Yeah, you can work on the board, you can work with partners.